Oh, hi. Hello there. I didn't see you coming, but I'm glad that you're here because let me ask you a question. Have you ever gazed at the night sky and wonder why are the color of the stars white? Or gazed at the sun and wondered why is it yellowish orange, right? If you ever ask yourself these questions, you're in luck because I'm about to explain it to you. Let's get right into it. Okay, but before I explain, there's something you should know. And that thing is called heat. You see, every object, even this marker that I'm holding, when they're heated high enough, they give off a certain amount of radiation. And this is important for later, so I'm gonna get back to it. But for now, let's go back to my initial question. What is heat? You see, different sciences like physics, chemistry, biology, they have different meanings for it. But for the sake of this video, I'm gonna keep it simple and clean. You see, heat is a type of energy that's caused by high temperature difference. But why is this important? Aren't we talking about the stars and the sun and their color? And yes, thank you for telling me this, because what I'm about to tell you is gonna explain it. You see, our sun is a good example of a black body system. But what is a black body system, right? What does it do? You see, black body systems absorb all the radiations that's nearby them. And this was explained by the smart people from the 19th century. Okay, so this law is called Rayleigh and Jean law. And this law explains the density of a black body system's wavelength. And the expression goes like this. But there's something wrong with this expression, and that is, it only works for the long wavelength. Okay, so as we know that the first equation is bad for the short wavelengths, right? So over time, there's a scientist called Mike Planck from 20th century. He came up with a solution for this problem, and the solution is so this is a new equation. You might be asking, isn't this just like complicated? Like, why does it make it better? So the answer is, if I were to take the limit that goes to 0 for both equations, this one and the old one, this equation actually goes to 0, which is what we want. But for the first one, something funky happens, and that is, it diverges and it goes to infinity, which is not what we want. No, that's a no-no. But these are just my words, right? So let's prove it right here, right now. Okay, let's start with Mike Planck's expression, which is this. But as you can see, it's really complicated, right? So why do I want to work with that? I don't. So what I do is I change my variables with letters. So for numerator, I have 8, pi, h, and c. I'm going to change them with letter a, as can be seen here. For my denominator, I'm going to change hc over kt with b. And that's going to simplify my life. And you'll see why in a bit. So when I do that, I get this expression. From here, my first step is to take the derivative of this expression. From there, I got this. You see, my numerator is fine, but on my denominator, I'm getting a fraction because of this thing. This thing. But it's fine, that's fine. Because what we're gonna do is we're gonna do a cool math trick, which is, you see, this is my main fraction, and this is my second fraction, the smaller one. I'm gonna flip the second one, and I'm gonna multiply it by the first one. Then I'm gonna take my variables in front of my whole expression. So from here, I have 5a over b, limit goes to infinity, my wavelength, and the rest of the expression. So from there, I'm gonna keep taking the derivative of it. But I don't have any space left here, so I'm just gonna put my work up here. And as you can see from my work, at the end, I'm getting this expression. And since I'm taking a limit of a denominator, my whole expression has to go to 0. Bam. For this part, what we're gonna do is we're gonna combine Mike Planck's law and Taylor's polynomial of EX law and derive to Riley and Jean's law. But how do we do this? First of all, let's take a look at Taylor's expression for EX. According to him, EX equals to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and this goes on for forever, and this is true for all of the x's. So, what do we do from here? We're going to replace our x with hc over wavelength kt. So let's do that. Let me just hc wavelength kt equals to 1 plus hc kt plus hc kt 2 factorial, and as I said, it goes on for forever. But the only part that we're gonna need is the first two, so let's go. I'm just gonna look at Mike Planck's law again. His expression is this. So I'm gonna replace the denominator with the expression that I got from Taylor's law. So let's do that real quick. So the numerator stays the same. So let's go. My that this is going to be 1 plus hc that kt minus 1. Okay, so we are good so far. So when I look at this expression, just smiley face, I can simplify a couple of things. Like I have a plus 1 here, I have negative 1, so they're just equal to 0, and I can simplify my HCs on my numerator and denominator. So let me just take them out. So my final expression is like this. Not final, but close to final. Just write this down. My wavelength and kt. Okay, so I have a fraction and I have another fraction. So what I can do is I can reverse the second fraction and multiply it by the first one. So this is exactly what I'm gonna do. So from here I get 8 pi, nothing changes, 5, and I'm reversing the second fraction like that. And it's just gonna be my wavelength. I'm just leaving this to make it simple, kt, and this equals to 8 pi, my wavelength to the negative 4, kt. And from here, we have one more step left. You see, we can make this expression look like this. T, my wavelength. Smiley face. There you go. I've done all these crazy maths, but how do I apply this? Well, for that, I have to look at my initial graph, which was radiation versus wavelength graph. You see, my radiation tops around 5,000 K, but the sun's temperature is 5,700 K. However, since it still falls on that range, it's gonna have 5,000 K's color. In this case, it's yellow. And that's the reason why the sun's color is yellow. I'm gonna show you another graph, a couple more graphs actually. But for that, I'm gonna take you to another room. Okay. My equation seems fine, so does my result. That's good, that's good. Wow, you're really good at this. Just saying. But I'm glad that you're here because for the next part, what I did is I took Mike Planck's equation and used it to get the peak value for the sun. So I'm just gonna put that right here. And with this, I'm gonna conclude my discussion about the sun. But how about the stars? I actually have a couple examples in mind, so let's take a look at it together. Okay, quickly. I'd like to explain the colors of the stars that I picked using intensity versus wavelength graph. The first star that I picked it's called Sirius, and its temperature is around 9200 K. According to a graph, it should have a blue color. The second star that I picked is called the Sun, and its temperature is around 5700 K, so it should have a yellow color. Lastly, the last star that I picked is called Betelgeuse, and its temperature is around 3400 K, so it should have a red color. Okay, let me ask you a question. How about any other object, including us humans? Will we also glow like the stars? Well, the answer is, in order for an object to glow like the stars, its temperature has to be high enough. But our body temperature is only 370 Kelvin, which is nowhere near high enough to glow like the stars. But don't be discouraged and be sad, because we can do other cool stuff, because we give off infrared radiations, which heats up objects that are nearby us. Actually, let me give you an example. I've been holding this pen for a while now to draw all these pictures, to write all these names. And when I first picked up this pen, it was cold, and now it's hot. And I think it's real cool to be able to heat stuff by just touching it. It's really magnificent. To summarize this, in order for an object to glow like the stars, their temperature has to be high enough. And thank you for watching.